Hi, everybody. So the next unit that we're going to be getting into is our discussion of sugars. Now, sugars are arguably, I think that they're the most direct move from an organic chemistry class into a biochemistry class, just because of the fact that at the end of organic chemistry or throughout organic chemistry, you draw structures. You draw a bunch of structures, and well, here we are, the carbohydrates. They are a bunch of structures. So sugar, um, also known as saccharides, monosaccharides are your simplest sugars. They have a empirical formula of CXH2OX. So common examples of monosaccharides are glucose, fructose, ribose, galactose, glyceraldehyde. They all have that basic C6 or CXH2OX. Um, when we talk about larger sugars, it could be a triose, tetrose, or sorry, our nomenclature includes a triose, which is three carbons, a tetrose, which is four carbons, pentose is five carbons, hexose is six, heptose, an octose would be eight carbons. So that number, um, that prefix plus OSE indicates a sugar. Now, that prefix indicates the number of carbons in that sugar. Okay, so aldehydes are one functional group, and ketones are another functional group that are key to structures of sugars. Aldoses and ketoses are how those sugars are classified. So if you think about terminology associated with a sugar, you could have an aldo tetrose. That name right there shows that OSE, it's a sugar. Tetra means that it's four carbons, and aldo means that there's an aldehyde functional group. So these different sizes, we've got D-glyceraldehyde, D-threose, D-ribose, and D-glucose. These all are aldoses, um, but the numbers of carbons vary. We've got 3, 4, 5, and 6. What we're seeing here are the common names for these different molecules. What we're also seeing is that capital letter D indicating that this is a D stereoisomer. So yeah, 3, 4, 5, 6 carbons. So common sugars, like I said, fall into the category of being an aldose or a ketose. Glucose is an aldose, and this is your structure for glucose. So our aldehyde functional group, carbon number 1, 2, 3, 4, 5, 6. Whereas fructose, you do not have an aldehyde functional group. Instead, you have a ketone functional group. What is pretty common is it's somewhat commonplace for people to refer to fructose as the ketose version of glucose. And what that comes back to is the positioning of hydroxide groups. So for carbons number 3, so our numbering for fructose 1, 2, 3, 4, 5, 6. So the positioning of our hydroxide groups, carbon number 3 in both fructose and glucose have a hydroxide group on the left, 4 and 5 hydroxide group on the right. And there's there's our examples, aldehyde and ketone. Okay, so here are a couple more examples of different sugars and the common names that they have. D-ribose is an aldopentose. D-glucose is an aldohexose. D-fructose is a ketohexose. D-galactose is also an aldohexose. And D-mannose is also an aldohexose. So D-glucose, galactose, and mannose are all examples of aldohexoses. D-ribose, glucose, galactose, and mannose are all examples of aldoses. Now, these four sugars that have been highlighted right here, well, they are all fairly similar to one another in that they all are D sugars, but what makes them different from one another is that two of them are aldohexoses, one is a ketohexose, and one is an aldopentose. Three of these molecules are going to have the same formula, molecular formula, but the positioning of different hydroxide groups is going to cause them to be differentiated from one another. So whenever you look at a sugar, it's always important to identify any chiral centers and see, okay, does this carbon have four unique things coming off of it? You've got glyceraldehyde here, and you have, well, glyceraldehyde on the left-hand side where you have a hydroxide group to the left. And then on the right side, this structure is a hydroxide group to the right. This is an asymmetric carbon. This is your asymmetric penultimate carbon. So your second highest numbered carbon. This figure on the left is the L configuration, and on the right is your D configuration. These two molecules are mirror images of one another. Now, oopsies. That L versus D configuration is a very important thing to reconcile and identify whenever you look at a sugar. D-glyceraldehyde versus L-glyceraldehyde. Okay, now when we look at glucose, you can identify the penultimate carbon. Well, second highest number, this is 6 carbons, so your second highest numbered carbon is going to be this one right here, where I'm drawing an X. I'm going to erase my X and just leave the dot behind. That's carbon number 5. 6 carbons, the second highest number is carbon number 5. But how many asymmetric centers, how many chiral centers are on here? Well, here's one, here's one, here's one, and here's one. This has a total of 4 asymmetric centers, or 4 chiral centers. Now, that penultimate one, when the hydroxide group is on the right-hand side, that is going to indicate the D versus L configuration. So your penultimate or your second highest numbered carbon is going to say that D configuration or L configuration. When sugars are mirror images of one another, they are called enantiomers. If you look on the left-hand side, we have our D configuration of glucose, and on the right-hand side, we have the mirror image of that, which is the L configuration. So L and D sugars, so L-glyceraldehyde and D-glyceraldehyde are enantiomers of one another. D-glucose and L-glucose are enantiomers of one another. Diastereomers are the same chemical type and size, but they are not mirror images. So here what we have is D-glucose and D-gulose. If you look at these two sugars, well, one thing that's worth noting is that they are both D configuration. So in carbon number 5, they both have a hydroxide group on the right-hand side of the molecule. Carbon number 4 and carbon number 3, however, in carbon number 4, D-gulose has a hydroxide on the left-hand side, glucose on the right-hand side. Carbon number 3, hydroxide on the right-hand side of gulose, and it's on the left-hand side of glucose. So this is an example of two sugars that have two variations. So two asymmetric carbons are different from one another. Now, here what we have is D-glucose and D-galactose. These two sugars are different at only one position. Carbon number 4, D-glucose, has a hydroxide group on the right-hand side, whereas D-galactose has a hydroxide group on the left-hand side. These are referred to as epimers of one another. Specifically, these are C4 epimers. Okay, so whenever we have a sugar, it's always important to think about the biologically relevant form of that sugar. And whenever we think about that, what we need to recognize is a hydroxide group has lone pairs of electrons. In addition to that, so it can act as as a good nucleophile. In addition to that, we have this carbon number 1 on our sugars, where we've got something that arguably is a good electrophile because that carbon in our aldehyde functional group has a double bonded oxygen. That double bonded oxygen is going to have a partial negative charge to it, meaning this is going to be partial positive. Each of these groups down here, partial negatives. So those partial negatives are going to be attracted to that partial positive, and they're in close proximity to one another spatially. So they'll be able to kind of hone in on one another and basically make a cyclic sugar, something like that. Now, what's worth noting whenever we have this sort of model right here is this oxygen right here. Okay, so we have carbon number 1, 2, 3, 4, 5, 6. So we have made a ring where an oxygen is a key part of that ring. Our carbon numbering has not changed. Carbon number 1. What has changed, however, is that carbon number 1 no longer is an aldehyde. Instead, carbon number 1 has a alkyl chain. It has an oxygen making an ester. Then we've got a hydroxide group and a hydrogen. So when we think about this carbon right here is achiral. But when we make this ring, now this is a chiral carbon. We'll come back to that in a little while, but I just want you to think about that. So carbon number 1 is chiral, and whenever we've made a ring, whereas in the linear form, it's achiral. So it's a new asymmetric center. This is called an anomeric carbon. Now, to put this all into perspective and to kind of visualize all of these different sugars, here are all of the aldoses. I've taken this figure that has a total of 5 sugars highlighted: glyceraldehyde, ribose, glucose, mannose, galactose. Those are the 5 that I want you to know the structures of. I want you to know the relationships between those sugars. For instance, if you look at glucose and mannose, what's the difference between glucose and mannose? They're both D sugars because they both have the hydroxide group on the right-hand side of carbon number 5. Carbon number 4, they both have a hydroxide group on the right-hand side. Carbon number 3, they both have a hydroxide group on the left-hand side. Carbon number 2, they both have a hydroxide group on the left-hand side. Or, I'm sorry, carbon number 2, mannose has a hydroxide group on the left-hand side, and glucose has a hydroxide group on the right-hand side. So these are molecules that are differ only about one position, and that makes them enantiomersive, epimers of one another, specifically C2 epimers. So I want you to know those structures, I want you to know the differences, and I want you to know the similarities. But these are the 5 aldoses that I want you to know the structures for. Okay, now with that, here are all of the other aldohexoses: allose, altros, glucose, mannose, gulose, inose, galactose, and talose. Sorry. And a mnemonic: all altruists gladly make gum in gallon tanks. So this is a figure that's worthwhile, though, because I think you can look at this and say, okay, if you wanted to know all of the structures, which I'm not expecting you to know, altros is going to have hydroxide there. Okay. Then glucose. And then So I thought, you basically can fill this in to get better at learning the structures. Personally, the way that I have learned the structures of the sugars is I start with glucose. And I look at glucose and I say, okay, am I drawing D-glucose? I am. If I'm drawing a linear D-glucose, that means my hydroxide group on carbon number 5 is on the right-hand side. Carbons 2, 3, and 4, right, left, right. Okay? I know that. It's on the right-hand side, left-hand side, right-hand side. That's going to be my structure for glucose. I don't need to worry about the positioning of any atoms on carbon number 1 or on carbon number 6. I need to only worry about 2, 3, and 4. So as long as I'm drawing a D sugar and I have glucose as a reference, I can draw that and then look at anything else and say, is it a C3 epimer of glucose? Is it a C4 epimer of glucose? What is it with respect to glucose? And I can go from there. Now, here are your examples for ketoses. Dihydroxyacetone is a very simple ketose. It's your simplest ketose. It's a triose. It is a ketose. Dihydroxyacetone is the specific name for it. Now, if you look below that, we've got our first 4-carbon ketose, D-erythulose. But the structures that I want you to be able to identify is D-fructose, D-ribulose, and D-hydroxyacetone. So if you can do those, then you're in good shape in my book. And then over here, like I said, D-glyceraldehyde, D-ribose, D-glucose, D-mannose. So recognize these in the linear form, be able to say something about what they look like, and then you're good. Back to the cyclization, though. We have 2 different ways in which a sugar can be cyclized. One way is with an aldehyde functional group. Your aldoses are going to follow this model, where an aldehyde is going to react with an alcohol to make a hemiacetal. That hemiacetal is going to react with another alcohol, potentially, to make an acetal. Now, when we're cyclizing one sugar, we basically just stop right here. We make a hemiacetal, and that's where it stops. But that hemiacetal remains capable of reacting to form an acetal. When we have a ketose, we have a ketone that reacts with an alcohol to make a hemiketal. That hemiketal remains capable of reacting with an alcohol to make a ketal. But again, when we're cyclizing one sugar, we're making a hemiketal. We're going to generally make either a 6 or a 5-member ring because your most common structures or your most common ring structures for stability is either a 6 or a 5-member ring. You can have rings that are larger than 6 or 5 members or smaller than 6 and 5 members, but their stability is going to go way down. So generally, we're making either a 6-member ring or a 5-member ring. If we look at monosaccharides, almost always are going to exist as 5 and 6-member rings. We've got glucopyranose on the left-hand side. We've got another version of glucopyranose on the right-hand side. That anomeric carbon, that newly formed chiral thinner at carbon number 1, right here and right here, is going to be pivotal for our nomenclature. So we've got D-glucose, carbon number 1, I've circled it. That carbon number 1 becomes our new chiral center. That new asymmetric center, carbon number 1 and carbon number 1 right here. So they are alpha D-glucopyranose and beta D-glucopyranose. So the relevance and the importance of this is basically looking at the hydroxide group that was previously our double bonded oxygen. What is that hydroxide group? Where is it? Is it pointing down or is it pointing up? If it's pointing down, that means you're dealing with alpha D-glucopyranose. If that hydroxide group is pointing up, you're dealing with beta D-glucopyranose. These 2 sugars, these alpha and beta D-glucopyranose, are anomers of one another. These are carbohydrates that differ only in the configuration of their anomeric carbons. So nothing else. These are not C2 epimers, they're not C3 epimers. The only variation between these two sugars is carbon number one. Where is that hydroxide group? So the two anomers can freely interconvert in solution. This is also known as mutorotation. And what ultimately we see is that the beta configuration is about 2-to-1 ratio of the alpha configuration. And that has to do with where that, excuse me, where that hydroxide group and where that carbon number 6, which if you look at carbon number 6, it's outside of our ring altogether, where that is positioned. Um, and that's going to dictate what type of, or the stability. So with all that in mind, though, here's an animation that shows the cyclization of our sugar. We're tracking carbon number 1 on the right-hand side. CHO is carbon number 1. That's our double bonded oxygen. That ultimately becomes that hydroxide group. And it's the hydroxide group on carbon number 5 that is the oxygen that is found within our ring. So it's a little bit, I know that it always ends up as a little bit of a confusion, but what I'd like to say is the oxygen in ring is C5OH group. And OH on C1 is the old, I'll just highlight it or put it in quotes as old, carbonyl oxygen. So that was a visual for our, that was a visual for the cyclization of a 6-membered aldose. Here what we have is the cyclization of fructose. And this is it's a nice color-coded model for, well, which is the atom that is, or which is the oxygen atom that's within our ring. Here you can see the hydroxide on carbon number 5. When we cyclize it and go to form our alpha D fructofuranose versus alpha D fructopyranose. So this is the 5-membered ring versus the 6-membered ring. What's happening? So we have the oxygen, the OH group on carbon number 5 forms, or is the oxygen within that ring to give us that alpha D fructofuranose. Then we've got alpha D fructopyranose. The oxygen within that ring is the oxygen of the OH group on carbon number 5. Carbon number 6, in both cases, is outside of our ring. Now, what's always kind of tricky about this is, and I'm sorry, whenever we form the fructopyranose, it's this hydroxide group. Correction here. Sorry. Okay, so this is C6 right here. C6 right here. Okay. Now, when we're cyclizing, we have the C5OH group reacting with carbon number 2 in order to form D-fructofuranose. In order to form fructopyranose, on the other hand, we have the hydroxide group on carbon number 6 that's reacting with the carbon on, or sorry, we're reacting with carbon number 2 on our main chain there. So this right here is the OH that I've circled right there. So that's the biggest difference between forming a 5 or a 6-membered ring. Which is the hydroxide group that is acting as our nucleophile? Is it from carbon number 5 or is it carbon number 6? Here, when we're forming a 5-membered ring, it is the hydroxide group on carbon number 5. When we're forming a 6-membered ring, it's the hydroxide group on carbon number 6. Now, what that means is that this right here is carbon 1. This right here is carbon 1. Carbon 1. Now, in both of these instances, we have our hydroxide group pointing downward on our new anomeric carbon, which in this case is carbon number 2. This is carbon 2. This is still carbon 2. Hydroxide group pointing down indicates alpha configuration. Alpha configuration. Okay, so these are commonly known as Hayworth structures. This is your convention for drawing a sugar. The way that I personally like to start out by drawing a Hayworth structure is I draw 2 parallel lines in oxygen, and then I draw a point. I draw another. There we go. There's my 6-membered ring. Carbon number 6. And I'm just drawing glucose because that's pretty much the most common sugar structure that you're going to jump out with. Now, when I draw a Hayworth structure of glucose, I'm just going to draw my arrows or my lines to show where my hydroxide groups are going. Carbon number 1, I drew my hydroxide group here, but again, that's something that I'm ready to flip up and draw like this, because that is just a carbon number 1 is, am I talking about alpha or a beta configuration? So I've got 2, 3, and 4 as my hydroxide groups. And they are going down, up, down. So when I'm drawing glucose, I'm taking my linear form of glucose that looks like this. One, 2, 3, 4, 5, 6. I'm going to draw, this is D-glucose, so on the right-hand side, carbon number 5, we've got hydroxide group. Then I've got on carbon 2, OH, carbon 3, it's on the left, carbon 4, it's on the right. So right, left, right. That translates to down, up, down. That's the way that I remember how to draw or convert a linear form of a sugar to a cyclic form of a sugar. And that will be essentially, you will need to be able to do that on your exam. Okay. So whether that hydroxide group is down or up, that's going to dictate whether you're talking about a alpha or a beta sugar. Okay. Some common furanoses, so 5-membered rings, fructofuranose and ribofuranose. Oh, sorry. Beta D fructofuranose. Notice how that hydroxide group on carbon number, that would be 2, is going up. That is a beta configuration. Our hydroxide group pointing up on carbon number 1 there, this is 1, because if you remember ribose, which I'm going to scroll back to, here's ribose. 1, 2, 3, 4, 5 carbons. That's carbon number 1. This is the hydroxide group, or the oxygen of the hydroxide group from carbon number 4. Where's the hydroxide group pointed? It's pointed up, hence we are dealing with a beta sugar. So These are common furanoses. It's important to remember that if you have a hexose, you can make a 5-membered ring. If you have a hexose, you can make a 6-membered ring. Conceivably, if you have a hexose, you can make a 7-membered ring. How common is a 7-membered ring in any system? It's low. 5 and 6-membered rings are the most stable form, so that's what things are going to migrate to. Now, our Hayworth projection is shown at the top of the screen, but chair and boat configurations of beta-D glucose are worth noting. The structure that I've shown is at the top, the Hayworth projection. Don't want you to get it mixed up. I'm going to scribble this hydroxide group out. Now, this is the beta configuration. The Hayworth configuration of beta-D glucose. On the left-hand side, you have your chair, and on the right-hand side, you have your boat configuration of beta-D glucose. So it's always worthwhile to think, okay, this is 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. So those two configurations are stable. That chair configuration is one that is important whenever we talk about, or for something like cellulose, which is tons and tons of glucose molecules making a very large structure. Okay, so these are a couple of different cyclic structures of glucose, and I gotta be honest, this is the most common. It's the most common, and it's the one I like the most. It's the easiest for me to decipher. I think it's the best for all of the reasons that I previously mentioned. If you open up any metabolism textbook or most metabolism textbooks, most biochemistry textbooks, you're going to see that Hayworth projection of glucose right there. The other three are relevant. You can get some information from them, but I think that number 2 there is the best and displays glucose the best. Okay, so the functional group on sugar, if you look at glucose displayed here, it's got tons of functional groups. Those functional groups can be reduced. Glucose, for example, can be reduced or can undergo reduction to be converted to a molecule known as sorbitol. So in this case, what we have is our aldehyde, or our carbon number 1, going from an aldehyde to having an alcohol. Sorbitol is produced naturally from glucose. It can be used as a sugar substitute because it's metabolized very slowly. Now, the natural production of glucose, or natural production due to elevated levels of glucose in diabetes, contributes to cataract formation and ultimately nerve damage. With that said, though, another sugar, ribose, here what we've got is D-ribose, our 5-membered aldose. Ribose can be reduced, and when ribose is reduced, it forms a molecule known as D2-deoxyribose. And the formation of that deoxyribose is essential for DNA synthesis, because if you remember, DNA stands for deoxyribose, or deoxyribonucleic acid. So there's your deoxyribose. Now, functional groups on sugars can also be oxidized. So when you think about reduction, think about forming an alcohol, or removal of an alcohol altogether. So functional groups on sugars can be oxidized. Sugars that become oxidized at the aldehyde functional group are known as reducing sugars. Oxidation of the aldehyde group of glucose is the basis of the blood glucose test meter. Glucose oxidase or glucose dehydrogenase convert glucopyranose to gluconolactone. The molecule shown here, of which the ring opens up to form a carboxylic acid from glucose. So when you think about the oxidation of glucose, think glucose oxidized to an acid. Okay. Now, hydroxyl groups of sugars can react with phosphates to form phosphoesters. So this is our third example of how a sugar can be modified. Here what we have is glucose 6-phosphate, D-glyceraldehyde 3-phosphate, and deoxyribose 5-phosphate. We've got, starting on the left-hand side there, I think that's the easiest one to start out with. We've got what we've already looked at. We've got a cyclic glucose. We've got a 6-membered ring. This is a pyranose. 6-membered ring, carbon 1, 2, 3, 4, 5, and 6. Carbon number 1 is an anomeric carbon. Our hydroxide group is pointing downward. Carbon number 2 is the hydroxide group is pointing downward. 2, 3, and 4 are the ones that ultimately are going to give us some indication of what type of sugar we're dealing with. So in a nutshell, whenever you want to draw a phosphorylated sugar, basically just replace the hydroxide group with OPO3. So here what we have is glucose 6-phosphate. And you can imagine if you wanted to draw glucose 4-phosphate or glucose 4,6-phosphate, it would be OPO3 2 minus. Okay. So there's two other examples, D-glyceraldehyde 3-phosphate and deoxyribose 5-phosphate. So hydroxyl groups of sugar can also be replaced with amino groups. For example, if you took something like this right here, N-acetyl manosamine and pyruvic acid, that molecule right here, this N-acetyl neuromanic acid, is hydrolyzed, and you end up with this molecule right here, N-acetyl neuromanic acid. This has that cyclic structure of a sugar because it is a sugar. It's a sugar with an amination at carbon number 4. It's a sugar that also has, actually that would be at carbon number 5, sorry, also has a carboxylic acid at carbon number 1. We've got an R group at carbon number 5. We've got a bunch of different things. Ultimately, this is a molecule known as sialic acid. This acts as a receptor for the influenza virus, or influenza viruses. And in a little bit less complex of a molecule, you have something like this down here, where you have NH2 and amine added to carbon number 2 of glucose and carbon number 2 of galactose, making alpha D glucosamine and alpha D galactosamine. Carbon number 2 has that amine group. So there's a number of different modifications to sugars that can be produced. And these sugars, or any sugar can be modified in a couple of different ways. It can be oxidized, it can be reduced, phosphorylated, it can be aminated. What I want you to know about is I want you to be able to identify these 5 specific examples. If I gave you the name versus the structure, what is this? Likewise, if you, speaking of this one right here, mannose 6-phosphate, fructose 1,6-bisphosphate, and basically thinking of phosphoesters and sugars, knowing the sugars that I expect you to know, if I gave you the structure of a doubly or triply phosphorylated sugar, would you be able to identify it? And so what I'm leaning towards there is if I gave you the structure of, let's go with, I hate to say glucose because that's seemingly too easy, I guess. if I gave you a cyclic structure of galactose, which is one of the five aldoses that I want you to know, and then I added phosphate groups to the cyclic form of galactose, could you pick that out? That's kind of what I'm getting at there. Um, so those are things that are valuable, because whenever you get into metabolism, you're going to save yourself a lot of time if you can identify fructose 1,6 bisphosphate versus fructose 2,6 bisphosphate. Um, there you go. There's another potential candidate question. Okay, so there we go on that. Glycosides are molecules that are, um, they can be very simple, they can be more complicated. Basically, what they have is the addition of a group, or the addition of an alcohol onto an anomeric carbon. Here, for instance, we have methanol, or ethanol actually, as it would be, ethanol being added to an anomeric carbon, resulting in this right here, more importantly, forming what's known as a glycosidic linkage or a glycosidic bond. Now, with that in play, we have a product of H2O that's released. But more than that, and what's really important is this is a means, or this is a way we can go back just a minute. And if you remember, I said whenever we cyclize a aldose or a ketose, we stop at a hemiketal or a hemiacetal. When that hemiacetal or hemiketal reacts with another alcohol, you form an acetal or a ketal. And that is the way that we form a glycosidic linkage. So those glycosidic linkages are the basis for the formation of, those are the basis for the formation of um, higher order structured sugars. Sorry, those two can skip out. So don't worry about sorbitol or sucralose. Glycosidic linkages are the way that we form disaccharides. Examples of disaccharides are sucrose, lactose, and maltose. Sucrose is a disaccharide made up of glucose and fructose. Lactose is a disaccharide made up of glucose and galactose. Maltose is glucose and glucose. Here is an example of a disaccharide that specifically is sucrose. What we have is a glycosidic linkage between carbon number 1 of glucose and carbon number 2, 3, 4, and 5 of our fructose. Oh, sorry, carbon number 1 and 2. 1 of glucose and 2 of fructose. Sorry, not 5. So what we have is those two anomeric carbons reacting with one another. This is an alpha 1 beta 2 glycosidic linkage. Sucrose, what we have displayed here, is we have our glucose monomer, carbon number 1 and carbon number 2 in on our fructose there. So lactose, maltose are displayed here, glucose and galactose, glucose and glucose. Beta 1,4 glycosidic linkage, and we've got an alpha 1,4 glycosidic linkage. Disaccharides and monosaccharides are important to distinguish between one another, and being able to identify glycosidic linkage is important. But what's also important is to identify a reducing or a non-reducing sugar, and a reducing or a non-reducing end of a sugar. So I think that looking at a molecule like ribose, we have our anomeric carbon, and that anomeric carbon is free and accessible to react with anything. If we compare and contrast that with here, this structure right here, I'm going to draw a circle around the anomeric carbon of the carbon number 1 in lactose, in one of our monomers of lactose. That glycosidic linkage is making a 1,4 glycosidic linkage. And that anomeric carbon is occupied. It is bound. It has found a link with another molecule. Therefore, it is not free. It is not accessible to react with something else. Compared to this one right here. It is free and available. Whenever I think of a glycosidic linkage and identifying a reducing end of a sugar, what I look for is oxygen, carbon, OH group. Oxygen, carbon, OH group. That could be in a straight line, or it could be in this kind of V structure right here. It depends on if the sugar is an alpha or beta configuration. But the way that I think about it is, could this end right here that I'm going to put a big star by, I'm not good at drawing stars. Yep, I'm not even going to, yeah. Where I put this star, could that interconvert from the alpha configuration, or from the beta as it's depicted, to the alpha configuration? And if the answer is yes, it could, well, then that is a reducing end. If the answer to that question is no, it could not, then that is not a reducing end. If we look at new star right here, that right there, that new star, could that open up and interconvert between the alpha and the beta configuration? It really could not, because in order for that to happen, this entire other sugar is going to have to migrate downward. And that's no trivial movement. It's just completely energetically unfavorable to do. And as you can imagine and see, when we talk about polysaccharide here, we're talking about long chains of sugars. So oligosaccharides, or examples of polysaccharides, are cellulose, glycogen, amylose, amylopectin, and chitin. Oligosaccharides are found in glycoproteins. They play roles in cellular identity, and they are generally fairly short. Polysaccharides are something that might play a structural role, or they might play like an energy saving role, storage role. For instance, glycogen in humans, or cellulose plays a structural role in plants. Cellulose is a repetition of linkages, or sorry, a repetition of glucose molecule after glucose molecule after glucose molecule. But what makes cellulose so unique is that it is in a beta configuration. What that allows is for, I'm going to draw, there's one strand, there's one straight chain of cellulose, here's another straight chain of cellulose, here's another straight chain of cellulose. These individual chains or strands of cellulose, what they're able to do is they're able to pack up right next to one another. And when they pack up right next to one another, they can hydrogen bond with one another. And when they hydrogen bond with one another, they form this super strong network, which is why we can't eat cellulose, which is why cellulose makes trees, which is why cellulose has structural integrity. So this is a polysaccharide. It's nothing but glucose molecules, but this dense network of hydrogen bonds allows these strands to bind super tight with one another. Beta 1,4 glycosidic linkages are what hold cellulose together. Amylose, on the other hand, it's, well, shorter strands of glucose, repetitive glucose, but they're all alpha 1,4 glycosidic linkages. Now, polysaccharides like amylopectin can get considerably longer and can have chains that have branch points that are much less frequent, but they're still alpha 1,4 like glycosidic linkages. And these branch points that are alpha-1,6 glycosidic linkages. Now, glycogen is a bunch of alpha-1,6 glycosidic linkages and alpha-1,4 glycosidic linkages, and you might think to yourself, well, that's the same thing as amylopectin, but it's not, because here what we have is we have every 30 to 50 or every 7 to 11. So these branch points are much more common. Branches are more common in glycogen. So the branch points are much more common in glycogen than in amylopectin. But there's still a bunch of glucose molecules. Okay. Now, chitin is an example of a modified polysaccharide. It is beta 1,4 glycosidic linkages, but with an amine. Now, chitin ultimately is something that is in the exoskeleton of a bunch of different insects. So it's going to have different properties than, say, something like glycogen. But at the end of the day, it's just this repetitive polysaccharide. Now, lectins are proteins that bind carbohydrates specifically. These are part of your innate immune response, innate immune system. Mannose binding lectin targets microbes, phytohemagglutinins in plants. Polysaccharides are bound and used by binding to polysaccharides is commonly used by bacteria and viruses to attach to a cell so that they can get into that cell ultimately. Tamiflu, the drug that you get sometimes if you have test positive for the flu, inhibits a neuraminidase, which is necessary for the exit of the flu virus. Now, glycolipids are another derivative of a sugar, of a monosaccharide, but what they have on them is a lipid. So a lipid backbone. So here's your backbone for a lipid, but then you put this fatty acid here and a fatty acid there. So you have a sugar. A glycolipid is a sugar plus a pair of fatty acids. We're going to talk about these a little bit more in detail whenever we're talking about lipids, but cerebrosides are an example of a glycolipid. They consist of sphingosine and another fatty acid and a sugar structure attached to them. A sphingolipid backbone, a single sugar. That's all they are to make up a cerebroside. Those are important for neurological development and neurological function. Gangliosides, as you can see here, are basically that same thing with a much larger and intricate sugar structure. Complex carbohydrate plus a sphingolipid backbone. Glycosylation is the addition of a sugar to a protein. Glycosaminoglycans are polyanionic polymers of modified sugars. Okay, so let's extract that. Let's break that down a little bit. Polyanionic polymers of modified sugars. Okay, so we have a sugar that's been modified, and we have polymers of that modified sugar that have multiple negative charges on them. Peptidoglycans are peptides or proteins linked to polyanionic polymers of modified sugars. Glycoproteins are proteins linked to oligosaccharides. And all of these things, actually, we will talk about again when we talk about protein structure. Glycoproteins are proteins linked to oligosaccharides. and they fall into two different categories: N-linked or O-linked. N-linked glycoproteins are uh, modifications to proteins on the amino acid asparagine, or O-linked are joined to the amino acid serine or threonine. Now, the significance and the importance of glycosylation is how different or how cells differentiate. These are generally proteins that are on the exit. These are proteins that are generally displaying the sugar structure on the exterior of the cell surface. So a cell can be detected or sensed as something foreign based on the presence of these different glycosylations. In addition to that, these glycosylations are essential for distinguishing blood types. So basically, your blood groupings are determined, or your blood type is determined by the presence or absence of a glycosylation or glycosylations. So here what we have is group A, B, AB, and group O. Group A, you've got the A antigen on your red blood cell surface. Group B, you have the B antigen on your red blood cell surface. Group AB, you have A and B antigens on that. And group O, you have none of the antigens on your red blood cell surface. So, that's actually where I'm going to go ahead and, well, I'm going to continue. So, yeah, I'm going to stop there. There's a ton of information here when it comes to sugars. I want you to know anything that's on here is fair game, but I think that there's kind of a logistical consideration of prioritizing your information. Like, what's the most important information? You got to know the nomenclature. You got to know the structures. Be able to identify the structures, what makes the structures different from one another. Just rehash some old material like chirality, a chiral center, an achiral center, something that's chiral or not chiral. How many chiral centers does this molecule have? How many does this have? But then we brought up some new content. For instance, when we talked about, we gave a unique term to a new asymmetric center, an anomeric carbon. I asked you to know a total of 5 specific aldoses. But with that said, if I gave you the structure of allose, I would want you to tell me something about allose and what that structure is with respect to glucose. And I can see, looking at glucose versus allose, what's the singular difference? If you know the structure of glucose, you'll be able to recognize that carbon number 3 is the only difference between glucose and allose. And that is that there is a variation about carbon number 3. Therefore, this sugar is a C3 epimer of glucose. So there's some new terminology, but there's lots of old stuff, lots of stuff dating back to your organic chemistry course. But then there's other stuff thinking about partial charges. Yeah, so there's a lot here, but it's kind of bringing old stuff and just sort of updating it. At any rate, I hope this is helpful. If you have any questions, please don't hesitate to ask. Have a good one.